So I'm after Platschorre. I'm a Klarman Fellow at Cornell University, and generically the sort of brand of research that I'm interested in is that I take developments on the sort of more formal side of theory, such for instance these generalized symmetries, and I try to apply them to phenomenological questions such as the nature or the mass of new particle candidates. I'm really happy to have the opportunity to talk to you here, because I'm meeting you, but also because it allows me to escape sort of the storms that are currently raging across the northeast and be in a bit of a nicer climate. What I'll be talking about today is very much sort of in line with that ethos that I just told you about. It's some work of mine with Mario Rieck and Vasya Loratz, who I think also gave a seminar here in December on, this is about a very different topic, on obtaining axions that have two key properties. One is that they will have an exponentially high quality, and two is that they have a very predictive cosmological scenario. And I'll sort of spend the next 5 minutes probably sort of motivating why one is interested in an axion of this nature, but also what I mean by these things. As you're well aware, there's a sort of ever-growing experimental program looking at axions, the QCD axion, given how compelling they are as sort of candidates for several standard model puzzles or cosmological puzzles such as the nature of dark matter or the strong CP probe, etc. Now, for the QCD axion in particular, most of these searches are smaller scale resonant searches that are very finely tuned around the QCD axion mass in order to find it. What that means is that sort of by design, all these experiments have to take a very long time to sort of scan the entire QCD axion mass parameter space. So what we're talking about here is something on the order of decades. Okay. So the holy grail of axion physics is to provide an estimate, or at least sort of a benchmark for the axion mass to sort of speed up this process. Okay. Now, one common observable that is used to estimate the mass of the axion is the axion's cosmological influence. So it's, for instance, its local energy density. Okay. So the axion's local energy density is 0.4 GeV per centimeter cubed times 5.7 microelectronvolts over its mass times 706 times 8 squared. And what that means is that if you equate the axion's energy density to the observed amount of dark matter in our universe, then you get an estimate for the mass of the axion. Okay. Now there are three sort of important caveats to the statement I just made, and those are going to dominate our discussion for today. Okay. So the first caveat is that you want your axion to be of high quality. For the QCD axion, you have in mind that it solves the strong CP problem, and what that means is that the dominant contributions to this axion's potential come through QCD effects, and any other effect has to be extremely suppressed. Okay. So that's what I mean by high quality today. The dominant effect to this axion's potential are QCD effects. Okay. The second caveat is that I haven't explained this last part of the formula yet. So this is A initial. This is the initial angle. This is, sorry, that's not true. This is the difference between the angle that the axion enters its cosmology with versus the eventual minimum for this axion that's going to be generated by QCD effects. Okay, so it's a mismatch between these two angles, and it's called, in the literature, it's called the initial misalignment angle. Okay, so you need to have a prediction for this misalignment angle in order to have a prediction for your axion's energy density. Okay. So, and I'll refer to having a good prediction for that misalignment angle as a predictive cosmology. What I really mean is that you have a very good prediction over the initial conditions that your axion is entering the cosmology with. There's a third caveat, and that is numerical in nature, which is that in most conventional axion models, this is not the only contribution to the axion's energy density. There can be additional contributions from topological objects that sort of emerge throughout the axion's cosmological evolution, such as, for instance, axion domain walls, axion strings, etc. So there's a plus let me call it topo, contributions. And it turns out that in numerical simulations, these have actually been shown that they can be the dominant contributions to the axion energy density. Okay. Now, if you're trying to equate to the same amount of dark matter, and you now start including these topological contributions, that means that the mass of the axion is larger than you thought it was. And in fact, usually it pushes up from something in the micro electronvolt range to something in the 10 to 100 micro electronvolt range. So state-of-the-art numerical simulations are like 45, 50 micro electronvolt if you just include the strings.
Is there some, what, oh, I see. I mean, I mean, it seems like if these topological things really have a different origin, they could give you too much density and then the model's just ruled out. Why? So are you saying that they always give you, I mean, there's some sweet spot where they give you of order the observed dark matter density so that they don't rule out the model but significantly change the axion mass?
You mean models for which the axion mass density had to be negative?
Yeah, of course that doesn't make sense. That just means the model's ruled out.
That is correct.
Yeah. So what I'm asking though is why is the topological contribution anywhere near the dark matter density? Why isn't it either orders of magnitude larger, in which case the model is ruled out, or orders of magnitude less, in which case this is still the prediction for the axion mass?
So that is a good question actually, because these are sort of set by QCD skills, whereas this is basically set by the UV of your axion model, so FA, etc., etc.
Yeah.
I wouldn't know why exactly these two are relatively commensurate in nature.
Okay.
What is the case is that, so for the strings, that is not the right answer. That is going to be my answer for these. There's also going to be a contribution from axion domain walls. And in that case, the physics is also set by QCD because that is what's providing the potential for the axion domain walls.
Okay.
Yeah, okay, that's going to be my answer. So this third caveat is a bit, for me, it's a bit numerical in nature. Given enough sort of computational power, this is resolvable. Whereas the first two caveats are more theoretical in nature. Okay. And to me, this provides a very nice point where sort of theory, experiment, and numerics all come together to sort of drive the future of physics. And that's why I'm interested in this. The issue that we're going to that we'll find ourselves with today is that sort of conventional axiom models have a bit of a tension between satisfying any of these two qualities. So models which have a very high quality often have a very poor prediction for this initial angle and the other way around. Okay. To just illustrate that, complex scalar axions often have a very poor quality. They're very sensitive to UV physics, at least for the QCD axiom, whereas they have a very good prediction for this initial angle, at least in the best case scenarios. I'll illustrate that during the talk. Similarly, if we're talking about other conventional axion models, such as, for instance, extra-dimensional axions, they have a very high quality, but we'll find that they have a very poor prediction for this initial angle. In fact, it will be completely undetermined. Okay. So, as there, so that's our job to resolve. And what we'll find is that the axions which have both of these nice qualities are exactly the axions which are sort of mixes of these complex scalar axions and these extra-dimensional axions. Okay. Where that sort of mixing in the IR looks simple, but in the UV you're sort of mixing something extra-dimensional with something that is localized, for instance a complex scalar. And we'll find that we'll need a sort of generalization of what in string theory is known as the Green-Schwarz mechanism, which nowadays falls under the name higher groups, which is why we're calling these higher axions. Okay. The outline of the talk is therefore, first I want to go over these sort of conventional axiom models, so complex scalar axions and extra-dimensional axions, and their quality and their cosmological predictivity. Then I want to introduce these sort of mixed axions that are sort of the best of both worlds. And then if time permits, I want to move on to sketch in string theory how you might be able to get these axions out. Okay? Turns out that all the ingredients that we need to get these axions with these nice properties are present in string theory, but we'll get issues from other aspects related to string theory, such as supersymmetry. Okay? I think that is sort of the outline of what I wanted to do today. Are there any questions at this point?
Are you gonna explain why is there 7/6 for a power?
No, this follows from detailed numerical simulations of what happens as the temperature gets close to the QCD scale for that. No, sorry. Good. So the first conventional axiom model that I want to go over is these complex scalar axioms. So what I have in mind with complex scalar axioms is that there's an axion which is sort of the Goldstone boson of a spontaneously broken U1 symmetry that belongs to some complex scalar. So we have a complex scalar phi, and it breaks to some phi times e theta a, where a is the axion. Today what we'll always have in mind is that this phi is below the reading temperature of the universe, which means that after inflation, after inflation, the symmetry is still in the sort of restored phase, and it's only broken much later as the temperature starts dropping. And that turns out it's a sort of the best case scenario for these complex scalars. Okay, so just to run through sort of its cosmological evolution. Today it's a bit uninteresting what happens when the temperature is still above the value of this complex scalar, so when we're in the restored phase. But as the temperature drops below the value of this complex scalar, we're suddenly in a phase where the U1 symmetry is spontaneously broken. Okay. This means that the axion suddenly emerges as a degree of freedom in our cosmology, and in every Hubble patch it will take some distinct value. For instance, in this one it's A is 0, this one is A is pi, etc., etc. Every causally disconnected Hubble patch it will take a different value. Then the temperature drops further and further. At some point QCD effects turn on and all these axions start rolling towards the minimum generated by QCD. Now, what is going to help us in this scenario is that our Hubble patch today actually makes up a very, very large number of these initial Hubble patches at this early time. Okay. So, just to illustrate that, that's our Hubble patch today. So what that means is that the initial axion value we see is actually the average over a very large number of initial axion values. Okay. So what we can do in this case is, because these initial axion values in this scenario were uniformly distributed, we can do a statistical inference for the axion value we see, which is just the average over some uniform distribution. And what we get out is that A squared initial is pi squared over 3. Okay. So in this sort of post-inflationary scenarios, the scenario where this symmetry is only broken after inflation, we have a very, very good prediction for this initial axion value. So when we gain some, we lose some, and this is inequality of these complex scalar axions. Okay. So consider your generic sort of EFT rules. We want to write down a Lagrangian involving this complex scalar. Okay. And then we should write down all terms which are compatible with the symmetries of our model. Now, we already know that QCD is going to break the U1 symmetry of this model. Okay. And what that means is that we have to write down all the operators which break sort of the U1 symmetry of this complex scalar. So for instance, we have to write down operators phi to the n over 1 over some cutoff scale, which you can take lambda to the n minus 4. Okay. So our Lagrangian will have to involve these operators. Now it turns out for the QCD axion, these operators need to be suppressed to a very high degree in order to still satisfy the strong CP problem. So depending on depending on this VEF, this can range from, these have to be suppressed to order 8 to they have to be suppressed to order 12. Okay.
I mean, by these rules, you should write down phi squared as well, right? And then you don't even have an axion. So,
yeah,
I mean, I'm not clear what these rules that we're playing by are. I guess I'm asking.
So it is correct that you have to write down, you would have to write down a mass squared for the axion, like this?
Lambda.
But that doesn't
I want you to say that's lambda.
Lambda squared?
Yeah. Now you don't have an axion.
No, so I completely agree.
Lambda's like M Planck.
That's
or
just
something.
the Mexican hat potential then. If it's a Goldstone
No,
boson.
No,
this
this breaks the U1
This is
symmetry.
phi squared plus Hermitian conjugate, not
Oh.
magnitude phi squared. These are explicit U1 breaking things.
So
This is what people call the quality problem. And somehow they don't worry about the positive ones.
I say you should worry about this, and
Yeah.
this is to me part of the quality problem.
Okay. So naturalness, part of the also.
So, very good cosmology, very poor quality for these complex scalar axion models.
I mean, this doesn't take into account the fact that the U1 symmetry becomes a good symmetry if you like, GQCD goes to 0 or lambda QCD goes to 0, right?
Up to gravitational effects. So it isn't. So it can also be the case that sort of the U1 symmetry of the complex scalar is broken by gravitational effects, independent of.
I mean, at this level of, okay, why don't you go on, because there's many fixes for that. I mean, but anyway, go ahead. I'll see. Let's see what you're doing. Let's see what you're doing. Because, okay.
So that sort of covers the complex scalar scenario for me, unless there are further questions about complex scalar.
Okay.
So does axion within itself propagate information slower than the speed of light? Because we know the Hubble patch should be like somehow expanded so we can have no horizon problem. So everything within our Hubble patch should be similar. That's what the horizon problem is solved, or
So within these sort of initial Hubble patches, you can't have a correlation which is much larger than the speed of light at the point that the axion emerges,
yeah.
because the axion didn't sort of exist before that. So now you can't have so if these are really causally disconnected, they couldn't have a similar axion value. Well, there can't be a correlation between the different axion values. Is that the question you were asking?
I'm just thinking if we want to solve the horizon problem with inflation, then everything within our causal path should be pretty much the same value, no? Unless somehow axion patch is formed by some wavelengths shorter than.
Your worries in sort of inflating to a constant axion value? Or what is it? What is the setup that you would like to see?
I'm just
The
now.
fraction till after inflation.
Oh, okay, I see.
Well, so now we're going to see axions that appear during inflation. So we're now going to go over these extra dimensional axions now. And I want to keep contrasting this to sort of the complex scalar scenario. Okay. So with these extra dimensional scenarios, what I have in mind is sort of the simplest sort of Minkowski space, and on top of it you put an extra dimensional circle, like that. And that circle has some angular coordinate phi, which ranges between 0 and 2 pi. And in fact, what I'm going to do is, because it's sort of the best case, I'm going to start identifying opposite sides of the circle. So I'm identifying phi and minus phi. Okay. Effectively, what that does for us is it cuts the circle in half, and we have two endpoints. Okay. These endpoints are special in the sense that they didn't transform under this phi and minus phi symmetry at this time. Eventually, I'll start putting matter fields at these endpoints. But for now, I'm just interested in getting an extra dimensional axion out. Now, in order to get an extra dimensional axion out, what you do is you introduce a bulk gauge field. A, which has some gauge identification, A is the same as A plus D of lambda. Okay. Now, to a low energy observer, the only thing you see is sort of the average over the extra dimensional circle. Okay. So what that means for us is that we're going to see the average of the gauge field over the extra dimensional circle, which exactly gives us one axion. Okay. So the Arnold-Bohm phase of the gauge field around the extra dimensional circle is our axion, And this gauge transformation actually becomes the 2 pi symmetry of this axion. So A is the same as A plus 2 pi. And in that sense, the axion is sort of the lowest gauge field imaginable. Now, just as the complex scalar scenario, this axion can have a shift symmetry, where axion goes to axion plus constant. Okay? But, in contrast to this complex scalar scenario, we'll see that the UV completion actually gives us a better handle on the symmetry. Okay? So in the UV, this axiom came from integrating a bulk gauge field. So that bulk gauge field must have a symmetry, A goes to A plus constant, that reduces to this constant shift symmetry of the axiom. Okay? And what I mean by constant is sort of the D of that thing is 0. Okay. This is not a gauge transformation. I would not be able to write this as the D of something. Now, in order to sort of appreciate that this symmetry is better in some way than this symmetry is, let's just study the sort of objects that are charged under the symmetry. So the only gauge invariant objects in the gauge theory are Wilson lines. Okay. So we have these Wilson lines, which are like e to the I, the integral of A. And under this symmetry, what happens is that they get transformed by a U1 phase times e to the I, the integral of A. Okay. Now, very important, these Wilson lines are one-dimensional objects. Okay? And the symmetry is therefore acting on sort of a one-dimensional line operator. In contrast to, in the complex scalar case, where it was acting on a zero-dimensional field. Okay? So nowadays, these symmetries fall under this sort of generalized symmetries program. And since they act not on zero-dimensional objects, but one-dimensional objects, they're called one-form symmetries. And since it's a U1 phase that I'm transforming by, they're called U1 one-form symmetries, which to everyone's delight has been abbreviated to U1 with a 1 on top. Now, to appreciate that these symmetries offer you a bit more protection than sort of in the complex scalar scenario, imagine anything that contributes to the breaking of this axion shift symmetry. Okay? Because an axion is the Aharonov-Bohm phase of the gauge field around the extra dimension. The only effect that is sensitive to Aharonov-Bohm phases are things that wrap the entire extra dimension. Okay? So what that means is that any effect contributing to the breaking of this axion's potential will definitely be suppressed by e to the minus the action to sort of wrap this extra dimension. Now, if, for instance, you had some bulk fermion which has mass m, and the size of this extra dimensional circle is r, what that means is that you'll get a suppression e to the minus m times r in your potential, necessarily for any effect which had a bulk mass.
So I just, since I'm not so familiar with this language, if you just told me that you wanted to have this symmetry, and I didn't know anything about generalized symmetries or one-form symmetries, which in fact I don't, I would just say, oh, okay, so if you want to have this symmetry, what you're really telling me is that you want to have no charged matter in the bulk, and then you could somehow try to break it on the boundary. I mean, I guess I'm asking, is there a more conventional way of talking about this without talking about what you're going to tell us, without talking about one-form symmetries?
So to me, you could have also appreciated the fact that this axion gains some additional protection in the UV because it's like an Aharonov-Bohm phase of the gauge field. And then you can,
right,
if you want, lose out on sort of this information of the U1. But necessarily that sort of translates to the same thing where you get an axion which has a symmetry which is exponentially well protected. So that is why, to me, sort of the underlying message of, well, that's because this axion shift symmetry was actually a zero-form symmetry acting on the axion that came down from a sort of one-form symmetry in the x dimension. To me, that tells me that I get an exponential suppression, and it's sort of encapsulating this entire story into one set of lines. Is that sort of what you were asking, or were you?
Yeah, I think that's right. So this is reminiscent. Yeah, right. This is sort of like, yeah, right. This is similar to like the radion, which is also this non-local mode, which therefore is has quite a bit of protection.
Exactly. And to me, the only protection comes from the fact that I've told you what the UV realization of my theory is.
Mm-hmm.
Okay. And that is what I'm trying to indicate with these extra-dimensional axions and the exponential quality. What I've been doing is I've been telling you about the UV realization, which offers me more protection than the complex scalars. Well, I also gave you the UV realization there, but that's pretty cool.
Okay.
So when we think about these extra-dimensional axions, we just think exponentially higher quality in this case. And the suppression is in mass times radius of the size. Now, to appreciate that what we've gained in quality, we've sort of lost in cosmological predictivity, consider again this extra-dimensional axion, and consider reheating at temperatures much above the inverse size of the circle. Okay, that means that you're going to have to deal with all the additional KK modes of the gauge field, but the average of the gauge field is still a well-defined parameter. Okay, even in this phase. So what that means is that, for instance, this axiom was also around during inflation. Okay, so during inflation, we have these Hubble patches again, and the axiom takes some distinct values in each Hubble patch, A0, A pi, etc. But now the exact opposite is going to happen of what happened to us in the complex scalar case, because our Hubble patch is actually a very small Hubble patch in one of these initial Hubble patches. Okay, so just to indicate that is us.
Sorry, maybe I just missed this. Maybe you said it, or maybe it's obvious. But anyway, why is it that in this scenario you're considering the case where the axion exists before inflation?
So I'm saying that it will exist before inflation, because this average of the gauge field is unless you had, if you tag on another UV completion on top. But to me, as long as the extra-dimensional circle remains an extra-dimensional circle, I can talk about the average of the gauge field over that circle, and it's still well defined.
It depends on the size of the extra dimension versus the inflation scale.
How so?
Well, if this scale is very, very small, if the extra dimensional scale is very, very small, compared, the energy scale associated with that is very high compared to the inflation scale, you can do all of this stuff before inflation, right? Then you just have a U1 gauge field during it, or U1 Goldstone boson during inflation. But on the other hand, if it's the other way around, if the inflation scale is low compared to the size of the extra dimension, then you have to do inflation in some 5-dimensional world, right?
So I'm saying the issue is not the inflationary temperature versus the size of the extra-dimensional circle. Even if you reheat above the inverse size of the extra-dimensional circle, the axion is still around as a degree of freedom in this model.
Sure, the axion is, right. But this extra-dimensional structure depends on whether you're looking above or below the...
Yeah, but the additional KK modes will not, you provide additional sort of initial conditions for these KK modes, but that doesn't matter. Like, you're providing me with an initial condition during inflation for the axion, and it will be around during inflation. Like, whether you have to care about the KK modes or not is not a...
Okay.
So that's a scenario, so this initial angle is completely undetermined, basically. Okay. Even worse, you don't know what sort of the distribution of axion values during inflation was. So we're sort of left with what I would say is no cosmological predictivity. That just to answer, because there is actually a scenario where this axiom stops to exist as a degree of freedom. Okay. So just like with the complex scalar case, if the VEF goes to 0, that is when the axiom stops existing as a degree of freedom. And basically you can see the breakdown in the Lagrangian because you get your kinetic term scales like this, f squared times d of the axion. In this scenario, your kinetic term scales like 1 over r times d of a squared. So if the extra dimension decompactifies at any point during the cosmological evolution, then the axion, which is the average over the circular size, stops existing as a degree of freedoms, right? So if the circle sort of breaks up, that is when you no longer have the axion, when it goes down to a flat extra dimension. So that is a way to get out of having these axions always be pre-inflationary if you have a transition from flat to compact extra dimensions after inflation. But I don't consider that to be sort of part of the standard paradigm. Which I think was closer in line maybe with what you were saying, sort of imagine a restoration of the symmetry during inflation.
Yeah, I don't know. I mean, I don't. I guess. Okay. Why don't you go ahead and finish?
No worries.
Yeah.
So we gain some, we lose some. I should also say with the complex scalar scenarios, there's been a lot of work into trying to get the symmetry to be higher. To be of better quality. And most of these models, broadly speaking, they always involve assigning gauge charges to different parts of your theory in order to sort of remove lower dimensional operators up to a certain order. Okay? So these are these Zn axion models or composite axion models. And even though you're sort of polynomially gaining quality, what ends up happening is that you lose predictivity because you start introducing relic densities or additional massless fields into your cosmological evolution or axion domain walls, etc. So you gain some, but you lose some is sort of the general statement.
In the complex scalar case, if f is bigger than the heating temperature, then you have both problems.
Yeah, that's the worst case scenario. Because also, so the gravitational effects scale like f over m Planck, for instance. So if f becomes very close to m Planck, so you're really much above sort of inflationary scales, then you start running into real issues. Yes. I think I'll just remove this because I don't like talking in a corner. So, having sort of seen the best and worst of both of these scenarios, let's try to work towards the resolution. And the punchline is that we're going to mix these two to get the best out of them. Okay. So in the IR, what I'll start with is I'll start with one of these complex scalar axions, which I denote as u1 to the 0, because it was the zero form symmetry. And I'll also have one of these extra dimensional axions. Okay. So let's start with having both of these axions around. And then, in order to end up with just one axiom, what we'll do is we'll gauge a diagonal combination between the two symmetries. Okay. So we introduce an additional gauge field, and we gauge just some diagonal between the two symmetries. So this is U1, this is U1, and we gauge some diagonal. And let's call this gauge field C, and CS in gauge identification. Okay. Now to convince you that this axiom has these nice properties, let's first consider its quality. So suppose you have any effect that, so this is, of course, if you have two U1s and you gauge the diagonal, you're left with one axiom. So consider any effect that would break this U1 symmetry. Okay. Since I can never break the gauge direction, I always have to break exactly the orthogonal direction. Which means that I always have to break this exponentially good symmetry. Okay. So I receive this, I sort of inherit this exponential protection for this new U1 symmetry. I will call this PQ for the axiom. To sort of appreciate that this axiom has...
Sorry, so if I just added one of your higher dimension operators there for the U10 axion,
Yes.
that seems like that would...
That's not gauge invariant.
Oh, I see, right.
So the only gauge invariant operators you get is like a complex scalar times e to the IA basically, and then you receive the exponential protection
Right.
from there.
Right. Okay, thanks.
To appreciate that, sort of, we've returned to a cosmology in which we have a good prediction for this angle. Consider again reheating above this U10. Okay. At that point, what you have is you have a complex scalar and a massive gauge field. Okay. So there's no initial angle. There's no axion degree of freedom that you can define in this case. Now the temperature drops below the temperature of this VEF, and at this point, the axion emerges as sort of the difference between the two phases. Let's call this B. Then the axion emerges as the difference between the two phases, and you can write down a gauge invariant prediction for sort of the axion. So you're back in this sort of post-inflationary scenario where the axion only emerges as a degree of freedom much after inflation, temperature-wise. Okay. Any questions about sort of this sort of thingy? Okay. Now, in UV, things are a bit more tricky, and that is because you're trying to gauge a gauge field under the gauge transformations of another gauge field. Okay. So one of these axions was one of these x-dimensional axions, which was some sort of bulk gauge field in the UV. So what does it mean to gauge that bulk gauge field under the gauge transformations of some other gauge field? Okay. So the UV model I have in mind is you can play different games. This extra-dimensional interval again, and we put the complex scalar phi and c at the endpoints of the extra-dimensional interval. Okay. Now, for this sort of extra-dimensional axion, the only way to gauge it that is sort of compatible with the localization of C is to do something like A5, where A5 is the fifth dimension, A5 plus delta x5, where delta x5 is this point on the extra-dimensional interval, times lambda C. Okay, this is the only thing that you can really write down. And indeed, if you calculate this, bless you, then the axion transforms like this. Okay, it's just the integral of this thing which picks up the delta function. So this looks a bit wacky. Okay, and what we're going to need in order to set up things like this is a generalization of the Green-Schwarz mechanism. Okay, so I want to spend 2 minutes telling you what sort of the Green-Schwarz mechanism is in string theory. So the Green-Schwarz mechanism in string theory involves a field with two indices, B mu nu, which is sort of the analog of A, or it's going to be the analog of A for us. And B mu nu transforms under the gauge transformations of some gauge field C times some extra-dimensional gauge field F tilde, where F tilde is the field strength of some additional extra-dimensional gauge field that I introduced. Okay. Now in string theory, generically what you have is you have an extra-dimensional manifold, but on that extra-dimensional manifold you also have fluxes. Okay? And what a flux is it's basically a solution to the classical equation of motion, where F tilde is a delta function around that point. Okay? So you have an isolated contribution to the flux at this point. So that is quite generic in string theory, and this sort of Green-Schwarz mechanism led to the second superstring revolution. Now, the analog, or sort of the generalization we're going to need, is everything but with one index lower. Okay? So we have some gauge field, A mu. That gauge field A mu shifts by lambda c times the d of something, and instead of it being a gauge field, it has one less index, so it's the d of alpha, where alpha is some periodic scalar. So alpha, as it says, alpha plus 2 pi. Okay. Now if you set up your extra-dimensional theory, and on that you have a field which has a domain wall, so d of alpha is delta of x5, then you indeed return to a scenario where you have a delta function localized gauge transformation. Okay? And you can even imagine that, for instance, these fields are also localized on the same domain wall by some interactions they have with this periodic scalar. So that is a way to set up delta function localized gauge transformations. It's very interesting what also happens with anomalies in this case and how to sort of track that across. The way I learned about these things is in M theory, you have a very similar scenario. When instead of a one-form or a two-form field, it involves a three-form field. Okay. But you can localize gauge transformations by having extended objects in the x dimension. In this case, a domain one.
Isn't there a deconstruction story too for Green-Schwarz?
You mean, so you can write it in terms of AU?
Yeah.
One-dimensional?
Yeah.
I'm not familiar with it, but it should exist. I
To
wouldn't say that-
me this looks a lot like, I mean, if you just have something very simple where you just say, well, I just have a localized gauge field on a boundary. In a sense, you have the same sort of structure here, right? The gauge transformations are only fixed on the boundary. So now, if you just combine that with a bulk gauge group, you have gauge group on the boundary, gauge group in the bulk. You can certainly have Higgs fields on the brane that transform under both. You can break down to the diagonal. So I think this is exactly some equivalent to something like that, which is in turn equivalent to something like deconstruction.
Yeah. No, that would be
That's
very
what it
similar
looks
to
like to me.
deconstruction. Yeah. I just want to make it plausible so that you can get these delta function localized gauge transformations. Are there any questions at this point?
Sorry, can you remind me why we can have a domain wall for U1? Because I usually think of domain wall for like Z2 potential, and when I have a U1, I usually get a string for like the most basic case.
So if you have a particle which has a 2 pi periodicity,
Yeah.
you can certainly set up a domain wall that goes between 0 and 2 pi.
Oh, okay.
It is true that it is true that in this model you also have strings, and those can, in principle, quantum mechanically sort of break up the domain. If that was your question.
So it's more like the initial condition give to this domain wall. The domain wall
Exactly.
itself is not like the lowest NG solution.
Well, you can set it up such that it is, but for now, what I just have in mind is that I already provided you with an x-dimensional structure, and now I'm saying I'm also putting topological objects on top of that. So the x-dimensional structure is just an x-dimensional field theory with on it a domain wall.
Okay.
That is the statement.
I mean, is your setup not somehow equivalent to saying that you have a bulk U1 gauge group, you also have a boundary U1 gauge group, and then on the boundary you're Higgsing the boundary U1 cross the bulk U1 down to a diagonal U1. Isn't that the same as what you're doing?
It would give you the same number of degrees of freedom. I'm just checking.
It's different because you're saying this is an unbroken, this delta thing is an unbroken gauge symmetry, and then you're breaking that. Maybe you have to do one more step, but somehow I feel like there's a more conventional language that you could use here with just boundary.
So what I'm a bit
gauge
worried
fields
about
and
is that
boundary
if you start introducing
bulk
another
gauge
gauge field, you end up with 2 degrees of freedom in the low energy IR field.
Well,
Like-
one of them is going to be, the thing that's Higgs. So just like in a complete theory, maybe your boundary has more structure, so this theory has a little bit more structure, right? Your theory is the low energy version of this when you integrate out the massive. What I'm saying is that your A5 is an unbroken. Isn't this right? Is an unbroken gauge symmetry when you break.
I'm not entirely
You're
sure
breaking these two gauge groups down to the diagonal. So there is a massive gauge mode that's not in your thing there, right? That would be like the structure of the boundary or something.
So there's a massive gauge mode, which basically that C ends up being massive.
Yeah,
Because it eats the diagonal of this combination.
right.
I'm not sure that this model is exactly equivalent. I would have to look at it after the thing. It might be. I just have to take a look at it.
All right.
So, having done sort of this low energy stuff, it is time to do a bit of string theory because I still have 15 minutes. And what I sort of want to do is not necessarily write down a string theory model, which you can find in our paper, but instead sketch sort of how all these ingredients come out of string theory and then sketch what the additional complications are that also come out of string theory. Okay. The reason you might be interested in this is that so string theory predicts axions just from extra-dimensional physics involving gauge fields, just like here. And string theory might be the only, axions might be one of the only sort of low IR probes that we have with string theory. And it turns out that they carry several things from the UV down. Okay, so one of the things is sort of the number of extra-dimensional cycles, so the number of averages you can do. Another thing is, for instance, if your UV theory is a gut theory, then that means that in the IR there will be a relation between the axions coupling to photons and the axions coupling to GG tilde. And you can use that to provide a sort of bound in the axion mass, axion photon coupling parameter space. Okay? So axions provide a very nice IR way to test several aspects of your string theory. Okay? So
That's assuming the axion photon coupling is quantized.
No. I'm just the axion photon coupling versus mass in these sort of scenarios. There's a bound on sort of, since both the axion photon, so the axion photon coupling is FF tilde. The mass of the axion, assuming that most of it dominantly came from QCD, is GG tilde. In the UV, these two go to the same gauge group. And so there's an exact relation you can write down from the UV to IR, just depending on the level of embedding of these two symmetries in the UV gauge group.
I'm just thinking you can have different instanton contributions in each piece in general that will give you...
You're assuming the axion photon coupling also provides a mass for the axion?
No, but instantons can give couplings corrections.
I agree.
So you don't need to know the coupling of the
Okay.
photon to the axion for this to tell you something about the UV.
So in this case, what will happen is that the slope of the axion at 0 will be related to the mass of the axion. Okay. So there will indeed be high order corrections to the axion photon coupling, like suppressed by instanton. But if you calculate the slope of the axion photon coupling, this scenario will be related to the mass of the axion.
These are just linear axion photon couplings from the instanton.
Yes, and that will have a slope.
Yeah.
I'm saying that slope is determined by the is related to the GG tilde. You would calculate. There's no way around this. Like, it's a gut theory. Everything is just determined by the level of embedding of your symmetry, of the FF tilde and the GG tilde.
Let's talk about it later because no one else cares.
Yeah. Okay. I miss guys. So in string theory, the sort of low energy realization of string theory is an NS1 supergravity theory in 10 dimensions. Okay? And what that means is that you always have a two-form, this being nu, a graviton, and a dilaton. Okay? But you're stuck with 6 extra dimensions that you have to compactify. Okay? During this compactification, you want to preserve SUSY. And the reason you want to preserve SUSY is that otherwise your compactifications become wildly sort of unwieldy. Okay? SUSY gives you a lot of different relations between the different sort of particles in your spectrum, And you can, for instance, just compute the bosonic ones in order to understand the low energy spectrum. What that means is that the manifold you compactify on has to be special, and it has to be what is called a Calabi-Yau manifold. Okay? Calabi-Yau manifolds in general will have several different cycles of different sizes, so you can have 2 cycles, 4 cycles, etc., etc. And you can integrate this b mu nu over over, for instance, these 2-dimensional cycles. So every 2-dimensional cycle will give you an axion, just like before in the extra-dimensional scenario. Okay. Now, generically in string theory, you also get these complex scalars. You get them from, for instance, gauge fields localized around extra-dimensional fluxes, so they're zero modes, or you can get them from branes intersecting at a point, which gives you complex scalars. So these complex scalars are present, and generically you also have gauge fields. So what I'm trying to say is that all the necessary ingredients are sort of set out on the table for us to get these sort of higher axions, these nice mixes between these 2 axions. The issue is SUSY. So SUSY generically relates different scales across your theory. And one way that shows up is, for instance, the vacuum energy has to be 0. So all these different contributions to the vacuum energy have to cancel. Okay? If you have a gauge field in your theory, then you'll get additional contributions to the vacuum energy due to the fact that all these particles are charged. Okay? So this diagonal combination was charged. And what you get is a contribution to the vacuum energy, which is known as the d term. And the d term for complex scalars is just phi squared times that charge. And since you also involve these these particles in these extra-dimensional cycles are also charged, what you get is an additional contribution, which is sort of, I'm just going to write it down and then I'll tell you how it scales, which is more interesting to me. You get an additional contribution from the cycles, and roughly what it does is it scales with the inverse size of the cycle, okay, which is like the VEF of the complex scalar. The analog of the VEF of the complex scalar. Now, what that means is that if we want the vacuum energy has to be 0, these 2 have to exactly cancel in order for us to preserve SUSY. So generically, what that means is that the VEF of your complex scalar is going to be roughly set by the sort of scales that you have in your string theory. Okay, so generically the VEF of this complex scalar will be something like 10 to the 16, 10 to the 17 GeV, which is really, 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 really pushing the post-inflationary scenario for these scalars. Okay.
Usually the d terms you have, a sum over charges times phi squared for that charge, and then typically this is telling you that positive and negative VEV charged VEVs are the same, right?
Exactly.
But now here this UV contribution is you only have one.
No, you could have multiple fields. You could have multiple scalars.
But maybe they have the same sign. Otherwise, they could. But the point is, I guess the point is that there's a heavy field which is nonetheless charged and has this VEV. I can think of that UV contribution as coming from that.
Yes.
Okay.
So you are correct that you could cancel between 2 complex scalars, for instance, the d term, but that would set the size of the extra dimension to infinity in this case. Mm-hmm. So what is sort of the way around this is that on your supersymmetric moduli space, if you have multiple cycles contributing to the d term, so something that you were saying.
This is really somehow a contribution to the stabilizing these moduli.
Yes, in a way.
Right?
There's also...
Because really one of these things is a field, which is some modulus field. I don't know, kappa or something is your...
So this will scale as 1 over sort of the size of the cycle, which is 1 over... which is your moduli, one of these SUSY moduli.
Right.
So what I want to say is that exactly what you were saying. If you have multiple moduli fields, then what you can do is you can make this very small. So you can have an almost cancellation between the moduli fields. And what that means is that phi can also be very small. Okay. So on your moduli space, there are special regions, which are called split loci, where sort of the contribution of just the exponential parts to your d term can be made very small. Okay? That doesn't necessarily mean that you end up with one of these axions. You still have to show that your moduli are actually stabilized along these split loci, so that this is actually a solution of the equation of motion of these moduli. I'm just saying that near these split loci, which are also interesting enough in string theory for other reasons, what can end up happening is that phi can be made small regardless of the internal sizes of your manifold. Okay, exactly as Marcus was saying, that you get a cancellation to parts of your d term. So the next sort of step in this higher axion program is to show that numerically you get these axions out. So including, so at Cornell there's this very good program right now studying the axions that come out of string theory. And what I want to show is that, I hopefully want to show is that you also get these higher axions out. Because they are basically our best way of testing string theory, in the sense that we have a very good prediction for where their mass will lie, and then hopefully their properties can tell us something about the underlying string theory, or at least we can discover an axion. Okay. So, I think that sort of draws me, So I think that sort of draws me to my conclusion, which is that today I presented a model of axions that have sort of two of these key properties, being exponentially high quality, but also having a very predictive cosmological scenario. The sort of mechanism that we needed today was a generalization of the Green-Schwarz mechanism in order to make the UV make sense of our theories. In generalized symmetry language, that is nowadays known as higher groups, and that's why we call these things higher axions. Okay. Now the sort of ingredients are there in string theory in order to be able to realize these axions, and it's a matter of showing that they also agree with the sort of SUSY requirements of string theory to get these axions out, and hopefully open up this sort of stringy axiverse to sort of one of these post-inflationary scenarios. Okay, that's it.
Questions?
Is there any constraint how inflation must happen if you want to have this higher axions? Like it must be a zero one scalar zero inflation, or is a completely different topic?
No, it's not a different topic. So the most essential ingredient is the fact that you want your reheating temperature to be above the symmetry restoration scale of these axions, such that it's only broken after inflation.
Okay.
Apart from that, you're sort of, at least for what I talked about today, insensitive to this sort of inflationary scenario, because you just need this uniform distribution to be created after the spontaneous breakings. So one thing I didn't talk about is the fact that because you're eating one of these U1s, you also additionally always get a gauge boson on top of these axions. So you get one of these nice axions, but you also get a gauge boson on top. You might think that you can push the mass of that gauge boson as high as you like, but the quality will get worse and worse of your axion as you push the gauge boson up. So if you have an estimate for the size of the breaking contributions to the axion, then you can provide an upper bound for the sort of mass of this gauge field, and in that way sort of provide a nice prediction for these sort of higher axions. Like the fact that it needs this additional support from the gauge field, which is basically protecting it in some way.
So what mass do you get?
I don't know, because it depends on what contribution you would give me as the symmetry breaking one. So we could write down, for instance, the gravitational one, and then do a calculation for the mass of the gauge field, but I don't expect it to be very significant. I think you can still push it up quite a lot, because it's this exponential protection that you get from the X dimension, instead of sort of a polynomial one. I can do the actual calculation, but I don't have it right now.
I'm just wondering, is it below 100 or 100 TeV, or is it up at the Planck scale? Where it's not at the Planck scale, right? It's not at the F scale. What scale is it?
I wouldn't be able to do that in my head right now. But we would. It's not a question of. The Planck scale is not the only parameter in this problem. So you want to solve the strong CP problem. So that's a 10 to the minus 10. So I don't expect the mass of this gauge field to be necessarily pushed to the Planck scale, but actually much lower than that.
Yeah, so will it be observable?
I don't
in our
know.
lifetime?
I don't know is the answer. It also depends on what order you allow the breaking to sort of happen in the EFT. Like if you already write down, for instance, this contribution to the mass, which would be lambda squared, or you go higher in the...
But if I just do this simple one extra circle model,
Mm-hmm. So you can do an extra-dimensional circle, and you can, for instance, put a fermion on top with some mass, an extra-dimensional fermion. Then that will give you a contribution to the potential. And what ends up happening is that if you give me the mass of that fermion in the extra-dimension, then I can provide you with the size of this extra-dimensional circle, which basically sets all the other scales in the problem, such for instance the mass of this gauge field C. But you have to give me a size of the breaking you expect to happen for the axion, which will then translate to an upper bound on the mass of the additional gauge field you need for support.
A long time ago, I wrote down a model with U1 gauge field in extra dimension, and then but broken by two pieces at two boundaries.
Yes.
Then does that do something just like that?
So this model, so you mean this, and there's an e to the IA in the middle? Like this? So this model was recently looked at again by Giovanni and Rudin. I think they also cited you, so that's not an issue there. But indeed, this model also gives you this also gives you an exponentially well-protected axion for the exact same reasons, and you can also get a post-inflationary scenario out. That is completely correct. So these are sort of two different models to get the same sort of high quality and good prediction for cosmology.
so you knew everything in this talk already.
Yeah, it's not like I should not have been in front of what you should have done.
Any other questions? Okay, let's thank Arthur again.